All right, welcome to today's lesson on the rate law, which is extension of what we've been doing in looking at rates of reaction. The rate law is a numerical determination of how the rate of a reaction depends on the concentrations of the reactant. So let's write that in here. It's the relationship of the rate of the reaction. Oh, I need my pen. The rate of the reaction to the concentrations. I'm going to put the S in parentheses because sometimes you only have one. Concentrations of the reactants. And what we're doing now is we're leading up to the next lesson. This is going to help us to understand what the mechanism, the way a reaction works, how that mechanism works. And we'll see that in the next lesson. So we like to use these generic reactions in which the small letter is the coefficient and the large letter is the chemical that we're looking at. And in general, for a reaction like this, we'll get a rate law, which looks like this, that the rate of the reaction is equal to little k times the concentration of A to some power x times the concentration of B to some power y. And the little k is called the rate constant, and it's considered to be the proportionality constant, between the reaction rate and the concentrations of the reactants. Oh. Now, seriously? Okay, I don't know if you saw that. My screen went blank because I hit something weird, and now we're back. So the rate constant K, which is normally indicated by a lowercase k, and if it's typed out, it will be italicized like this, depends on the nature of the reactants and the temperature. If we're doing this right, it should be independent. I'm not sure why I've got that much blank in there. It should be independent of the concentration, and that's going to be important so that we can actually change concentrations, as you see later on, and figure out what the rate law is. The exponents x and y are called the reaction order for each of the reactants, respectively, A and B. Now, be careful, X and Y are generally not the stoichiometric coefficients. So X is not going to be little a, B is not going to be little b. Now, not necessarily. It does happen sometimes, but if it does, it's a coincidence. Instead, what we're going to have to do is determine these exponents experimentally. And that's basically what we're going to be doing in our lab this week, next week as well. Now, x and y are usually integers. Equal to 0, 1, or 2. Having 3 or 4 is rare, and those stand for 0 order, 0, first, or second order. That's how we talk about it, 0, first, or second order reactions. We can have half orders sometimes. So half orders, like 1.5, 2.5. They're uncommon, but they're not unheard of, and we're unlikely to run into them in this class. And finally, the overall reaction order. So a reaction also has an overall reaction order. Is just the sum of the reaction orders of X and Y. Now, sometimes you'll be asked to determine the reaction rate, the reaction order, and the rate law graphically. You can do this easily for a reaction with only one reactant, or if you do other things to keep something else constant. As long as you have a pretty constant concentration of your other reactant, then this will work. And if we plot the rate of the reaction on the y-axis, so here's our initial rate. So we're always going to look at the initial rate because it's the easiest one to measure, and the initial concentration because that's the easiest one to measure. We set up an experiment so we know what their initial concentration of the reactant is, and then we change the initial concentration, and we plot it and see what happens. If it's a first order reaction, and you know what? Let me change colors to match what's going on. First order reaction. Then the rate is going to equal that lowercase k times the concentration of A to the first power. Okay, so that first power indicates the order is first order. And so what that basically is a straight line with slope equal to k. And so over here, this green line, we see our first order where the rate equals k times the concentration of A. And you don't have to put the 1 in there. That's going to be implied. All right, so a line because we have the k as the slope. So we'd be able to measure k, measure the slope. And the k in this case, we're going to see that it's going to have, the rate is going to be in molar per second divided by molar. So we have molar per second divided by molar. And the rate constant is going to be in units of seconds to the -1. And we're going to get more into that in a little bit. Switching colors. If the rate is second order, look what color I'm using. This should make sense now. The rate law is going to be that the rate equals k times the concentration of A squared. There's the 2, the second order, and that is the equation of a parabola with a parabolic coefficient equal to A. So, I'm sorry, equal to k. So we have here that the rate of second order for the red line, for the red curve, the rate is equal to k times A squared. And the rate constant k is going to be in molar per second is the rate. But now we're going to have to divide by molar squared, and you'll see how that works in a few minutes. And so we're going to get seconds to the -1, molar to the -1 as our unit for the rate constant k. Finally, we have this unusual situation, and we'll see how this works when we talk about mechanisms, where we have a zero order reaction. In a zero order reaction, the rate is going to equal k times A to the 0 power. I'm putting that in there to show you that that's just k by itself, k times 1, where the rate does not depend on A. Now, there's something we do have to draw in here. It always happens. We have to say, well, you have to have some concentration of A. So if your concentration is 0, you won't get any reaction. But the minute you get any A, then the reaction rate is going to jump up to whatever it is. And then the K is just going to equal whatever the concentration is. K is just going to equal the rate, sorry, not the concentration. And the rate is going to equal K times A to the 0. And since that rate is in molar per second, we have a unit of molar per second for the rate constant K. So the units for K are always going to depend on the overall reaction order, and we'll see more of that below, where the unit for the rate is always going to be molar divided by time for some time unit, and we'll talk a little bit more about that down below. So graphically, we can see what the rate law is based on the shape of the curve. If you have more than one reactant, though, then you might have to do a little bit more work. So we can make a set of data, and this is another thing you're going to do in the lab, in which we plot the initial rate of a reaction at different concentrations of each reactant. And we're going to use this to determine the rate law. And here's how we're going to think about it. Think about it in terms of the functions. If we have a first order reaction, then the change in the rate as you change the concentrations, the change in the rate is going to be the same as the change in concentration. Now, that is, make sure we're always going to keep all other reactants constant. So you're only changing one reactant at a time. And so what that means is, as we saw above, that the rate is equal to concentration of A to the first power. So if the rate doubles and you double the concentration, that's an indication of a first order reaction. Or if you triple the concentration, you should triple the rate. So if the rate matches the change in the concentration, then we have a first order reaction. In a second order reaction, the change in the rate is going to be the square of the change in concentration, just like we saw above. So we're going to say that the rate is equal to the concentration of A squared. So we're going to see a rate change of a factor of 4 if we double the concentration. Or we'll see a rate change of a factor of 9 if we triple the concentration, and so forth. So whatever you do to the concentration, you're going to see that squared coming up in the rate law, in the determination. And finally, if we have a zero order reaction, then the rate does not change. As the concentration changes. And so the rate is going to equal x to the 0 power. And so x to the 0 power is always 1. So the rate is going to stay the same if we double the concentration or triple the concentration. The rate is always going to stay the same. So that 1, that 4, and that 2, those are the relative changes. And we'll see how that works in the next example. So turn the page, and let's do an example where we've got two reactants, A and B, and we're going to make the A2B molecule out of them. And we've done a set of experiments, and in these experiments, we started off with initial concentrations of A and B as 0.1 molar each, and we got a rate of 1 times 10 to the minus 2 molar per second. And then in reaction number 2, we doubled the concentration of A while keeping the concentration of B the same. And then in reaction number 3, we doubled the concentration of B. Let me go back to the first one, while keeping the concentration of A back to 0.1 molar. And so what we're going to do is use those two comparisons to figure out what the reaction order is in A and what the reaction order is in B. So going to experiments 1 and 2, because we've changed the concentration of A and kept the concentration of B the same, that's going to give us the rate order for the reactant A. So we can see that in this reaction, in experiment 2, the rate doubled. So the rate went up by a factor of 2 when the concentration of A also doubled. So if you think about that mathematically, what do you have? You have the rate is equal to the concentration. The change in the rate, doubling, is equal to the change in the concentration to the first power. So what that means is that the rate is proportional to the concentration of A to the first power. And so x equals 1, and that's a first order reaction. To obtain y, which is the exponent for b, we're going to look at experiments 1 and 3. So comparing rate 3 to rate 1, what we can see is that the rate 3 is equal to 4 times rate 1. That's another way of thinking about it, 4 times rate 1. So that means that the concentration of B3 is equal, since the concentration of B3 is equal to 2 times the concentration of B in reaction 1, we have that 4 is equal to 2 squared. So the rate is proportional to the concentration of B squared. And so Y equals 2. And that makes this a second order reaction, or second order reactant. So now putting it all together, if I just ask you for the rate law, what you're going to do is you're going to take those two and put them together in something that looks like this, that the rate is equal to K. We don't know K yet. That's okay. The rate law doesn't have to have K in it unless I specify include the value and units of K, is equal to K times the concentration of A to the first power times the concentration of B squared, or you can just say K is equal to, let me make that bracket a little better, A times the concentration of B squared. Okay, so notice first order in A, second order in B, and overall reaction order is going to equal to 1 plus 2, or third order overall. So you're not going to have anything much more difficult than that. Hopefully that all makes sense. Now, we do need to find K because we're going to use K in a subsequent calculation to find out what the rate should be at any given concentrations of A and B. So to find K, you're going to select any experiment. It doesn't matter which one you do. In this case, these data are coming out perfect. In practice, if you were doing an experiment, you would find the rate constant for all the experiments and then average them. But finding it for this one is enough. So we're going to use the concentrations that we know, the X and Y that we know, and the rate that we know. We're going to solve for K, and we're going to watch out. Make sure you include units in your K because that's an important factor here. So let's plug in to the equation 1. So in equation 1, let's plug into the rate law. We have that the rate is 1.0 times 10 squared, 10 to the minus 2. Yeah, watch out, that sometimes will happen if you're not careful. And the units are molar per second. That's going to equal K times the concentration of A, which was 0.10 molar, times the concentration of B, which was 0.10 molar quantity squared. So rearranging that, we get that K is equal to 1.0 times 10 to the minus 2 molar per second. Divide that by, now let's do the math. We have 1 times 10 to the minus 1 times 1 times 10 to the minus 1 squared is going to be 1.0 times 10 to the minus 3. And then we're going to have to take those units. Molar and molar squared is going to give us molar cubed in the denominator. Now notice what's going to happen with our units. The molar here is going to cancel out with one of those molars and give us molar squared in the denominator. 10 to the minus 2 divided by 10 to the minus 3 is just 10. And let's put a decimal point there for some sig figs. And your units are going to be per molar squared second. So you can put it that way. Or 10, the decimal point, molar to the negative 1 seconds to the negative 2. So now we've got our unit and value for K. We can finish this up by, before we get to that, by the way, I just want to point out that the K the units for K are always going to depend on the overall reaction order. So you saw first, second, and zero order up above, and here's a third order overall reaction. And notice we have seconds to the -1 here, but if you have whatever time unit you have minutes to the -1, don't convert to seconds. You can keep it in minutes or hours or days or whatever you're given, unless the units are mismatched. And I'm not sure when that would ever happen, but if you do get mismatched units, then you're going to want to convert to a more convenient unit. All right, now that we have our rate law and we have the K, now we can plug in to find out what the reaction rate will be if we've changed the A concentration to 0.15 molar and the B concentration to 0.13 molar. So let's bring down our rate law. Rate is equal to K times the concentration of A times the concentration of B squared. And so let's plug in for K, 10 per molar per second squared, times the concentration of A is 0.15 molar, and the concentration of B was 0.30 molar quantity squared. And if we do the math on that, let's do a little crossing out so we can see what's canceling here. Let's go back to green. So let's see. Oh, you know what? I got those units backwards, didn't I? Hopefully somebody saw that. It should be molar to the -2 and seconds to the -1. That's going to be a little bit better. All right, so molar to the -2 is going to cancel out. Let's cancel out the molar squared here, and that's going to leave us with molar per second. So molar per second is going to be our unit, which it should be. Always look for the rate to be in units of molar per time. And when you do the math, you get 0.135 molar per second. And look at where that fits up on the data table up above. This is always a good thing to do. In the data table up above, notice that we were in between the A and the B, in between the A concentrations, but we had a lot more B. And 0.135 is 13.5 times 10 to the -2, if you're going to look at it in terms of 10 to the -2. So your rate is way, way down here, which it should be. All right, let me go back so you can finish copying that. I hope you do well on the homework. It should be pretty straightforward, and just follow the examples that we've done here. Thank you, and see you next time in class.